Hello everybody! So this is going to be a video on the work energy problems and a review of what we learned about today through the Ed puzzle. Just the equations that we were presented with, what they mean, and how they broaden our ideas of energy. The first three problems on this worksheet have to do with work and power, and we are given those two equations right off the bat. We're given that work is equal to your force times your distance, and power is equal to your work over time. I feel that you are fully capable of doing number 1 through 3 on your own, just identifying what you're given in the problem. If you're given a force, if you're given a distance, if you're given a time, and what you need to solve for. If you do have trouble on these ones, please let me know. I'll be happy to reach out to you and talk with you of what you need to do. But I'm going to move on to number 4. And before we start going through number 4, let's just go through the equations that we learned about today. So again, this is energy, work, and power, what we learned about today. And we learned about gravitational potential energy. And the equation for gravitational potential energy looks something like this. So we have PE, grav, is equal to, and it depended on 3 things. It depended on your mass, the constant of gravitational attraction, which is G, and your height. Right? Because we'd rather have a ball of some sort drop from a lower height to cause less damage than a higher height, because a higher height would cause more damage. It has more potential energy. So the 3 things that potential energy depend on: mass, that gravitational constant, G, and height. And remember, G in this class is 10 meters per second squared. And just to refresh your memory, gravitational or energy, sorry, I should say gravitational potential energy, but energy in general is measured in joules. Okay, so that units for that is a capital J, and that is joules. And then we also talked about kinetic energy. And kinetic energy is equal to 1/2 mv squared. So kinetic energy changes depending on your mass and your speed. Now, energy is a scalar quantity, so it doesn't depend on your direction. What we want to know is the magnitude. So kinetic energy, 1/2 mv squared. So if you increase the mass, then you're going to have a higher kinetic energy. If you increase your speed, then you're going to have a higher kinetic energy. Okay, and it's going to be a square of your speed, so it's going to be a square of product for your kinetic energy there. And then we learned about mechanical energy. And mechanical energy is made up of potential energy and kinetic energy. So ME, which stands for mechanical energy, is made up of potential energy plus your kinetic energy. So we say that ME is equal to PE plus KE. And when it's all within one system and there's no external forces acting on the system, then we can use the conservation of energy. And this says that your mechanical energy initial is equal to your mechanical energy final. And we can break this down further by using this equation right up here. We can say that your potential energy initial plus your kinetic energy initial is equal to your potential energy final plus your kinetic energy final. And this might look familiar to you because we talked about the conservation of momentum. And we said, when something is conserved, then the products of that something is the same before and after. Okay, so we have something going on within our system where the potential and kinetic energy are changing throughout a certain given amount of time. But what we need to know is that the mechanical energy before is equal to the mechanical energy after. And remember that mechanical energy is made up of 2 things, potential and kinetic energy. So with that, we can say that our potential plus kinetic energy initial is equal to our potential plus kinetic energy final. Okay, and you can even break that down further by using the 2 equations up here at the top with your potential energy and kinetic energy. All right, so that's pretty much what we learned about today for energy. Now let's start talking about work. And work is defined as W equals force times D. So if you are applying a force over a given distance, then you are supplying work. But remember, this force has to be in the direction of motion. Okay, and that is a very important piece of information. The force has to be in the direction of motion. So if you're moving to the right and the force is acting vertical, then they are applying no work to the object. Like let's say that you're picking up a suitcase or something like that while also moving to the right. Well, if your force isn't acting to the right while you're like dragging the suitcase to the right, then you would be applying no work to that suitcase. The force has to be in the direction of motion. Check out that little image there with the suitcases. It's a person pulling a suitcase directly to the right. It's a person pulling the suitcase at an angle and then pulling the suitcase up vertically. Now the angle one, it's important to note that you have to break up the force into components. So again, you have your y and your x direction components. Remember that y is that rise, x is that run. So if you wanted to solve for the force that is acting on the pole for that angle, you can find the resultant. But what we care about is the force that is acting directly in parallel with the motion. So if you're going to the right, then we want to know what force is acting also to the right so that we can solve for the work that is being done to that suitcase. And then we started talking about power. All right, and power is the rate of which work is happening. Okay, so we have power is equal to work over time. All right, so how much work we are applying to the object divided by the time of which it took to be applied. So how much power we are actually supplying. Okay, so work is equal to force times distance. Power is equal to work over time. And this is pretty much the equations that we are given for today. And joules is a measurement of all, or is the units for all of this energy stuff and also this work. And then we measure power in watts. Okay. All right, so with that information down, let's go through number 4. So use the picture to finish the table. Use the ideas of mechanical energy and the conservation of energy. So the mechanical energy initial is equal to the mechanical energy final. So the first one, we are given the information that we need. We are given that the potential energy is 30 joules. So when it's sitting up rest, like let's say the ball is sitting up rest on top of the block, then we know the kinetic energy is 0 at the highest point. And the reason that it's 0 is because the object is not moving. And if the object isn't moving, then the velocity or the speed, because we don't care about direction, is equal to 0. So if we plugged in 0 into our kinetic energy equation right here, then our kinetic energy is going to be 0, but our potential energy is going to be 30 joules. And this is when we have to recognize, okay, well, potential energy is your mass times the gravitational attraction constant, g, times your height. Okay, so we have this height, we have g, and we have a mass, and we are given the potential energy at the top is 30 joules. Okay, so now let's move over to diagram 2. Now this is a different shape, it's a triangle, but what we have to recognize is that it's at the exact same height as the previous one, and it's the exact same mass. So the mass is the same, g is a constant, and h, or the height of which it's from the ground, is the exact same. So what we can say for this potential energy is that it's the exact same as the previous. It's that 30 joules. And now we go to the staircase one. Again, at the highest point, it's matching all of the levels of the previous diagrams. It's the same exact mass, and the height is the same, and it's still being acted upon by the gravitational attraction constant, g. So we can say that the potential energy of this object right up at the top of that staircase is going to be 30 joules as well. And then I gave you a little hint. Right, break up these sections in even distance increments. So let's say that at the top it's 3 meters, and at that staircase it's 2 meters, and at that first stair it's 1 meter. Okay, so we can now solve for what this potential energy is. If this is 3 meters long and we multiply it by g, which is 10, and let's just call this 1 kilogram, then we can solve for the potential energy at the top. Oh, sweet, it's 30 joules. But now the second rung, we said that that was 2 meters. So if we plug in 2 meters into there, we can recognize that the potential energy is going to be 20 joules. And then that last one is going to be 10 joules, and at the bottom it's going to be 0 because there's 0 height. If that still doesn't make sense, let me know, okay? And I'll give you some more examples with that. Now, this kinetic energy, we have to now identify that mechanical energy is equal to your potential energy plus your kinetic energy. So kinetic energy is still at play with all of these situations. It's just that at the top, at that peak height, the kinetic energy is 0 because the object is at rest. And this potential energy, again, at that peak height, it's 0. Again, at that peak height of the third one at the staircase, it is 0. But now, when the staircase distance is shortened, right, we still have to have the same mechanical energy. So this kinetic energy at staircase number 2 would actually be 10 joules in order for the conservation of, momentum, of energy to work. So now understanding those principles that the kinetic energy still makes up the mechanical energy, we need to understand that when the potential energy is equal to 0, then it all must be in kinetic energy. So the kinetic energy while this is falling is 30 joules as well. Okay, so now it's a little bit of a tougher problem, but I gave you hints throughout these to help you through this process. So all ramps are 5 meters high. So these are the ramps that we're talking about right here. And they're all 5 meters high. And we know that the kinetic energy of the block at the bottom of the ramp will be equal to the loss of the potential energy just from the conservation of energy. So we need to find the speed of the block at the ground level in each case. So do you recall from earlier chapters how long it takes something to fall a vertical distance of 5 meters from a position of rest, assuming g is 10 meters per second squared? And I gave you that equation right there. I said t is equal to your square root of 2d over g. And the reason that we get this is that d is equal to 1/2 gt squared. So if we wanted to solve for t, we would just need to rearrange that equation. And we get that idea of d is equal to 1/2 gt squared from the ideas of linear motion. So go back through that earlier chapter in order to find out more information on that if you forgot. So using this equation, what is the time? So really all we need to do is plug in this information. We know that g is a constant and we know that d is 5 meters. So we need to plug in that information in order to solve for the time. And then we need to use this information in order to solve for v. All right, again, g is a constant, it's 10 meters per second squared, so whatever time that you solve for at the top here, that's what your velocity is going to be. So this is when it gets a little bit harder to understand. And the reason that is because, well, you're like, Miss Brennan, these are at all different, angles and they're different shapes. How can I even begin to solve what kind of speed I'm looking at? And this is when we have to recognize that the conservation of energy cites that your potential energy plus your kinetic energy initial is equal to your potential energy plus kinetic energy final. So if we solved for the potential energy initial and solved it for what would that kinetic energy be at the bottom? Well, we just solved for that final speed right here. We just solved for that falling object's final speed. So that falling object's final speed was, I think it's 10 meters per second. Yeah, 10 meters per second. And again, we have to recognize that it's coming from the same height. It's coming from the same height. So the potential energy initial is all the same, which means that your kinetic energy at the bottom is all going to be the same. So it means that your speed at the bottom is all going to be the same. So for each case, you should also have the same for case 1 speed. Again, I know that's confusing. We're going to keep talking about it all week. All right, I hope this is a little bit helpful to you. Keep